This is such an important rule, the chain rule for differentiation. We use the chain rule to differentiate composite functions. That's things inside other things. So we've got 6x inside ln. We've got 2x squared minus 3x inside to the 4. We've got sine x inside 1 over. So we've got things inside things. They're called composite functions. And we differentiate composite functions using the chain rule. Now, there's two ways to think about it. I prefer the intuitive way. I don't think of this rule, which is the chain rule, but I don't think of that while I'm differentiating. I just differentiate using the chain rule. So how do we do that? We think of this thing inside, the 6x, the 2x squared minus 3x, the sine x. Think of it just as a box called blah. So this is ln blah. Blah to the 4, 1 over blah, or blah to the minus 1. Just blah, 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 basically. And then you just differentiate, pretending that there is no problem, pretending it just says ln x. The derivative of ln blah, blah, blah is 1 over blah, blah, blah. The derivative of blah, blah, blah to the 4 is 4 blah, blah, blah to the 3. The derivative of blah, blah, blah to the minus 1 is minus blah, blah, blah to the minus 2. So you basically just differentiate, and in your head you're going, yeah, whatever, whatever. Then you multiply by the derivative of that thing. So you kind of pretend it's not a problem, and then the acknowledgement, the chain rule, is that you just literally times by its derivative. So I'm going to show you how that works, and I think that's the best way of actually using the chain rule. So, for example, ln blah. How would we differentiate that? We'd get 1 over. So that's the initial starting point for the derivative. The derivative of ln of blah is 1 over blah. Now what the chain rule says is that to make this true, all I have to do now is multiply by the derivative of that blah. That's how it says it works. So this is going to equal 1 over 6x multiplied by 6. 6 is going to cancel, and we just get 1 over x. So there are some funny things that are going to happen and some things to point out here. And the funny thing here, which I use for funny thing, I'll just use black actually for funny thing. I'm just going to go note. So the derivative of ln x is 1 over x. And the derivative of ln 6x is also 1 over x. And students often think they've gone wrong because the 6 has disappeared. But this is true. The derivative of ln 6x is 1 over x. Why? Well, because I just used the chain rule to show you. But also think of it like this. Ln 6x, using the rules of logs, is ln 6 plus ln x. So what would happen if I differentiate that? Well, that's just a number, like differentiating 2. You get 0. And then what's the derivative of ln x? 1 over x. So that's another way of thinking about it. The fact that if you write it like that, then you differentiate it normally. You don't even need the chain rule. Then it pops out like that. Okay, let's try another one. What is the derivative of to the 4? It's 4 to the 3. Notice I'm just pretending there's no problem. So the derivative of blah, 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 blah to the 4 is 4 blah, 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 blah to the 3. Now that's not the end, obviously, because we now have to do timesing by the derivative times by the derivative. So now we have to go multiply by the derivative of the 2x squared minus 3x. The blah, the insidey bit. So altogether that's going to give us 2x squared minus 3x cubed multiplied by 4x minus 3. Okay, now I can do a little trick here. If I want to fully factorise, I can pull out this common factor of x, and I'm going to not make the common mistake that students often make. Okay, I did make it. I made it deliberately to show you. Here's the common mistake. If this x comes out of here, then it needs to have its cubed on it. And this is such a common mistake that I'm going to write it in red. Be careful. Careful when pulling things out when there's a power on it, or putting things in when there's a power on it. It can't go in there. If I had x and then 2x minus 3 cubed, I can't put that x in here and make 2x squared minus 3x all cubed. If it was cubed, then I can put it in, but when it goes in, the cube and the cube they both act, so the x can just go in on its own. Careful. So make sure that makes sense to you. Right, the last one, put it here. I'm going to write it as to the power of minus 1. So what's the derivative of to the power of minus 1? Well, the minus comes down and changes to a minus 2. Exactly the same as we've got here. Now, this is a very common proof question. You can prove the derivatives of sec, cosec, cot, and tan using the chain rule. And so I'm now going to prove, this here is cosec, isn't it? This is the derivative of cosec x. So by writing cosec x as 1 over sine x and then thinking about like this and using the chain rule, I can prove what the derivative of cosec x is. Right, let's go. d by dx, sine x to the minus 1, is going to be minus sine x to the minus 2. But chain rule times the derivative of the sine x. Okay, what is the derivative of sine x? It's cos x. So altogether we get minus 1 over sine squared x, that's that bit, times cos x. Now, normally we don't think of the derivative of cosec as being this. We think of it as cosec, derivative of cosec is minus cosec cot. So how come it looks nothing like this? Well, there's a little bit of fiddling required. 1 over sine x multiplied by cos x over sine x. There's the cos x, and I've split that sine squared up into sine and sine. And now you can see it. There's the cot and there's the cosec. And you can use a very, very similar technique to differentiate, what do we do there? Cosec, you could do sec, you could do tan, you could do, so you could do tan and the other three, sec, cosec, cot. Now, why is this so important? Because there are 3 big features of the course, which you will think of, first of all, until it clicks, as being separate topics from the chain rule. And actually they're not. Implicit differentiation literally is the chain rule. So when you do implicit differentiation, come back to this or have this piece of paper out and think, oh my goodness, yeah, it is the chain rule. It's not even using the chain rule, it is the chain rule. Parametric differentiation, so that's differentiating a parametric function, that uses the chain rule. But it doesn't look quite so much like this, it looks more like that. Connected rates of change, well, that is the chain rule. So all of these topics, when you organise your notes, you should maybe put these 3 behind the chain rule notes so that you can remember that those 3 are just literally uses of the chain rule. The other big use of the chain rule is when you integrate, because when you integrate, what you do is you don't integrate, you guess what was differentiated, and then you differentiate it using the chain rule. So at this point here, differentiate, you'll be using the chain rule, and that will tell you what pops out, so that you know how to adjust your original guess to get your integral. So I personally don't like using it like this, but I am going to show you to the side here what it would look like if I use this method, which is taught in schools a lot. So what you do is, where the box is, I'm going to define that to be u. So in this case, I'm going to write u equals 2x squared minus 3x. That's u equals the thing I was calling just blah. Right, now change all of them to a u in the function. So now I'm going to write it as y equals u to the 4. You can see that that u is just my box, but I'm specifically calling it u. Okay, find dy by du. Okay, so I'm going to differentiate this y with respect to this u. dy by du is 4u cubed. That's that bit there, look. 4u cubed. Now I also need to find du by dx. Here's u. So du by dx is 4x minus 3. There it is there, 4x minus 3, differentiating u. So it's just this way of making kind of more explicit what you're doing, but personally I think it makes it more complicated, and it's much easier to just go pull it down, take 1 off, times by the derivative. Pull it down, take 1 off, times by the derivative. Derivative of ln is 1 over, then times by the derivative. If you do want to do it this way, it's absolutely fine. You define the u, then you rewrite the function using u. You find dy by du and du by dx, and then you use the chain rule, which kind of, you can just make sense. These cancel these du's. Dy by, it's not really like that, but it's what it looks like. Dy by dx, dy by du by dx. The du's cancel, giving dy by dx. Now, I've got du by dx here, I've got dy by du here, so I multiply these together to get dy by dx. But I have to remember not to write u, I have to write 2x squared minus 3x. That's the dy by du. Oh no, I forgot the 4. 4u cubed, that's u, that goes there, and then du by dx is there, and then obviously it's exactly the same as this. And this blue bit here is what you might be taught in schools by introducing the u. It's perfectly okay, but just so that you know, you don't have to, you can do it like this. How to check it? Right, all derivatives, don't forget, you can check on your calculator. What you do is, say for example, say I wanted to check my answer here, I wasn't sure if that was right. You say option, calc, d by dx, or on the class whiz, it's in the top right somewhere, there's a d by dx button. You put the function in here, so my one is going to be ln, which is, where's ln there? Ln of 6x. On the class whiz, exactly the same, but it won't just tell you the derivative. It won't say the derivative is 1 over x, but you can say the derivative at any point. So I'm going to put in 2.5. Okay, so I'm doing what is the derivative, what's the gradient of the tangent to this function at this point, 2.5. Okay, apparently it's 0.4. Let's check what I think I would get, because I think this is the gradient. So if I put 2.5 into here, I should get the same. 1 over 2.5, I should get the same. I do. So all your differentiation, doesn't matter whether you're using chain product quotient rule, you can check using that button.